Here we have OpenStax Chapter 6, number 44. I'm going to label my carts A and B. That just helps me when I set up my equations. I'm also going to label these angles. This one is going to be theta A, and this one is going to be theta B. So I'm going to treat this the way that I treat normal problems, which is I'm going to draw a free body diagram for both of my objects, and I'm going to write a net force equation for both of my objects. They're asking me to calculate the acceleration and the tension. Those are two unknown variables. And those two unknown variables are going to show up in the in the net force equation for both my object A and my object B. So you can see that I will have two unknown variables, but I will have two equations to solve, so I should be able to solve for those two unknown variables. So let me start by drawing a free body diagram for object A. I'm going to draw it where my force of gravity, which in truth is pointing straight down, but I've broken that force of gravity into one component that goes perpendicular to the surface and one component that goes downhill. And then I've tilted my axes. So I'm starting with my free body diagram already with my gravity broken into components and my axes tilted. If you need more explanation of how to draw a free body diagram when an object is on an incline, go back to week 6 and watch the videos about objects on an incline. So I have, in this downhill direction, I have the mg sine theta, and then in the uphill direction, I have my tension. So that's what I have here. To the right is kind of like my uphill direction. For my object B, now that uphill direction is pointing to the left when I tilt my axes, and that downhill direction is pointing to the right. Okay, so again, this is just the way that I set up my axes when I do it. And in this picture, uphill is to the right, and in this one, uphill is to the left, because that's how these hills are oriented on in this diagram. So now that I have my free body diagram correct, I can write my net force equation. So let's first calculate the net force in the y direction for object A. So I'm looking at the net force in the y direction. In the positive y direction, I have my normal force. In the negative y direction, I have mg cosine theta, and there's the negative. My net force in the y direction is always, always, always equal to my mass times my acceleration in the y direction. But in this problem, there is no acceleration in the y direction. This cart is not going to accelerate in this direction like this. So because my acceleration in the y direction is 0, my net force in the y direction has to be 0. That lets me say that my normal force is equal to mg cosine theta. That should not be a surprise. Hopefully you've done enough problems now where you see almost all the time when an object is on an incline, the normal force is equal to mg cosine theta. Now in this problem, there's no friction. And because there's no friction, I don't really care what my normal force is. But if there were friction, we would need to know what our normal force is. So I just wanted to give you guys some practice solving for our normal force. Let's look at our net force in the x direction, because that's the one that involves the tension, and that's the one that's going to involve the acceleration of the cart. So my net force in the x direction, well, in the positive x direction I have t, and in the negative x direction I have mg sine theta. My net force in the x direction is always, always, always equal to my mass times my acceleration in the x direction. And so here I've plugged in all the values that I know. And here I've just simplified the math a little bit. And notice that I have two unknown variables, tension and acceleration. Whenever you have two unknown variables, you need a total of two equations to solve for those two unknown variables. And I can get my second equation by writing a net force equation for object B. So my net force in the y direction, everything looks the same as what I had here for object A. And now when I write my net force in the x direction for object B, in the positive x direction, I have the mg sine theta, and then in the negative x direction, I have t. So that's minus t. So this just kind of, these signs are opposite of what I have for object A. And then I have the mass times acceleration, because my net force in the x direction is always, always, always equal to my mass times my acceleration in the x direction. Here I've plugged in all the variables, and here I've just kind of simplified the math a little bit. Now I pause at this point because I want to think very carefully about the relationship between the acceleration of object A and the acceleration of object B. They're tied together by a rope, so I know that their magnitudes definitely have to be the same. But I want to take a moment to figure out what about the sign, okay? Meaning, I know the magnitude of the acceleration of A has to be equal to the magnitude of the acceleration of B, but I want to see, are they the same sign? If, I think based on the fact that this is heavier and this slope is steeper, that B is going to accelerate in this direction, which means that A would accelerate in this direction. And I just need to check to make sure do they have the same sign of their acceleration. Well, in this picture, if B accelerates downhill, that would be to the right, and that would be a positive value. And in this picture, that would mean A would accelerate uphill, which in this picture is also to the right, which also means it's a positive value. That means that both the acceleration of A and the acceleration of B should be positive numbers, and they should be exactly equal to each other. So I'm going to say the acceleration of A should equal the acceleration of B. And then I do a little fancy math here. This is extra fancy math. Don't worry about this if this bothers you. But these 3 lines here say I'm going to define something. And I'm defining a new variable that I'm just calling A. And what am I defining it as? It's just equal to A sub A and A sub B. So if that bothers you, just don't worry about that part. Once you know that this acceleration is equal to this acceleration, that should be enough for you. But I like to do this extra fancy little thing. Now, why did I make such a big deal about checking the signs of these? Well, there are some cases, and like the one we went over in the weekly video from week 7, it does sometimes happen that these accelerations are opposite in sign. Okay, for example, the example where we had a cart or just a mass moving horizontally connected to a rope, and then the other one was hanging down vertically. So go back and look at those examples of tension problems from week 7 to see cases when the 2 accelerations are opposite in sign. So because sometimes these accelerations are opposite in sign, I want to be really careful and check what case is it. And in this case, they both will have the same sign. Okay. So I'm going to take this equation, which has 2 unknown variables, and this equation, which has 2 unknown variables. I've changed, instead of calling this A sub A and this one A sub B, now I'm just calling them both A. And now I have 2 equations with the same 2 unknown variables. So if you make it this far, you get 9 out of 10 points because the rest is just algebra. All I need to do is solve this system of equations. So I would probably solve this one for t and get 59 plus 10a and plug in that value for t into here, which is what I've done here. So 117 minus, and then I solve this as 59 plus 10a for t. And then I solve for my acceleration. Now once I know my acceleration, I can come back and plug it into this expression, which I've done here, to solve for my tension.